Hello everyone, welcome to the second lecture of week 11. So in this lecture we will discuss about various modern large language models. Basically we will give an overview of these, and we will discuss what is the difference in the architecture from what we have studied in the general transformers. So we will discuss that in certain lectures. So this will be one of the lectures we will talk about architecture variations. So this will be the topics that we will be covering. So a high level overview of the popular models, and then we will talk about one particular variation, that is Zwicklu, instead of say the feed forward network that we have talked about. So how is that different, right? So we will talk about that. So this slide gives an overview of popular LLMs. So for example, so we talk about the encoder only model. So you have BERT, Roberta, and then there are other variants like Albert, DBERTA, XLNet. You can see even the number of parameters, and you see they were all in the range like less than 340 million, 355 million was the maximum, and they were around 2019, 2020, trained maximum of 2.2 trillion tokens. Then you have the decoder only models like GPT-1, GPT-2, we talked about these. Encoder decoder models like T5, MT5, BART, again they are not too many parameters, up to say 300 million max. Then you have the GPT family beyond GPT-2. So you have GPT-3, GPT-4, WebGPT, Codex, and they were quite large models. Like GPT-4 in terms of parameters, like it's like some trillion parameters. GPT-3 had many variations. There was one with 175 billion parameters that we talked about. Then you have the Llama family in the open source models, and you have the Llama models 1 and 2, and then there are many models that are coming from Llama, right? So there are Alpaca, Vicuna, Koala, they are based on Llama. Then you have Mistral, then there are other variations like Code Llama, Long Llama, and so on. Okay, and of course this is taken from the large language model survey paper that is up to a certain point in time. So this may not be the entire set of LLMs that you would see right now. So you would have Llama 3, 3.1, 3.2, etc. also. Then you have the Palm family, and then there are other popular LLMs where you can see Chinchilla is what we talked about. There are Gemini, there is DeepSeek, right, and so on. And you can see many of these are quite large. Like Gopher is 280 billion parameters, and yeah, I mean this Bloom is again 176 billion parameters, Lambda 137 billion parameters. And you can see like what is the base model on which they are built on, and so on. So these are some of the popular LLMs which involve both closed, open, and there are many ways you can categorize these, right? So let's see what are the different ways we can categorize an LLM, right? So this is again from the same survey paper. So if you talk about an LLM, we can categorize them in terms of the parameters, in terms of the type, originality, and the availability. The most common categorization you will see is in terms of parameters. So like again, I mean there would be many ways people will categorize this. This is one way that was shown in this survey paper. So if it has less than 1 billion parameters, this is called a small LM. Between 1 to 10 billion parameters, a medium LM. 10 to 100 billion, large LM, and more than 100 billion, you have a very large LM, right? So you can see, for example, our BERT model and all were small LMs, while GPT-3 will come here. Yeah, and then similarly Llama 2 with 7 billion would come in medium LM, right? But 70 billion will come in the large LM. So that is one categorization. Then you have another very important thing, that is availability. Are the weights publicly available or not? If the weights are publicly available, we can fine tune those. Otherwise, we cannot fine tune, we can only do prompting, right? So if the weights are not publicly available, they are called private models. And if the weights are publicly released, they are public models. Of course, even there are other variations like have they released the code or not, what is the license, right? And there are other things also with public release, but at least here we are saying if the weights are publicly released or not. Then the third one is the originality, whether they are the original models. So, that means they are pre-trained from scratch, or they are just the tuned models. So, you take a pre-trained model and further tune it, right. Like llama is a model, original model from scratch, while alpaca is based on llama. So, it's tuned based on llama, right. So, they are the tuned models. And then you have variation that you would understand from what we discussed about instruction fine tuning and making it an assistant. So, it is a foundational model. So, you can just talk about foundational model that has been pre-trained. So, no instruction fine tuning, no chat fine tuning like MPT 7 billion, the foundation model. But then you can do instruction fine tuning, right. So, they are also instruction fine tuned. So, this is an instruction model. So, typically in the name you will see model name and then an instruct. So, that means it has been instruction fine tuned, and if you can fine tune them also in chat data, they are called chat. So, now you have a chat data set. So, what is the difference? In an instruction fine tuned model, you can give an instruction for the task and can perform the task. In chat models, you can do multi-turn conversations. So, you can give instructions and you can even continue your conversation. So, these are the chat models. So, these are the various categorization that we can talk about in large language models. Now, I'll give a brief high level overview of some models. Like in open models, Mistral and Mixtral are very popular, created by Mistral AI, and their goal was a very strong and multilingual open language model, and they had done many speed optimization. One thing it was very popular for is their mixture of experts architecture that we had briefly discussed in our week 5. Now, what are the new things that they had in architecture? So, you see transformer is common, but they have separate embeddings, rope embeddings. Now, what are these, right? So, I mentioned this term, but how do these work and what is the formulation of this? We will discuss in this week. And then they do swiglu, right. So, rather than FFN with ReLU, they do swiglu. What is this again? This we will talk about in the same lecture. And they go for a context 4K, and they used a specific normalization called RMSNorm, not layer norm, right. And they have a sliding window attention. This we talked about, right. So, you can see and they have mixture of experts in the feed forward layer. So, what you see here, so while you retain the original transformer architecture, you made a lot of variations over the years, right. So, it is not exactly the same that we have studied in week 5, but the positional embedding has changed, the FFN has changed, mixture of expert has come in, the layer norm has been replaced by RMS norm. So, you see a lot of changes have been happening over the years, but I mean the base architecture is still transformers with lot of changes. And you see you can talk about the data, like here it includes more English and European languages. Now, let us see the Llama 2 model from Meta. Again, this was an open model, and they wanted to make a very have a lot of safeguards and chat fine tuning. So, in terms of architecture, you see a repetition. So, it is a transformer plus rope embeddings and swiglu and RMS norm. So, you see this looks like very standard nowadays with modern LMs. So, they use swiglu, RMS norm and rope, and we have to talk about these in detail. This has been trained on like public sources like roughly 2 trillion tokens. Then you have another model Quen that has become very popular from Alibaba Group. It is very strong multilingual, especially on English and Chinese, the original model, and they use a large vocabulary for multilingual support. So, in terms of architecture, you see the same thing, transformer plus rope plus swiglu, RMS norm. They had something additional called bias and attention layer. We will briefly see what is that, and yeah, again roughly 2-3 trillion tokens instruction data at pre-training time. So, these are some open models, and then let us talk about some closed models very briefly, like GPT-4 created by OpenAI, the de facto standard strong language model, like to compare anything for, and it has been tuned to be a very good chat based assistant. It can also accept image inputs, and you also have a function calling interface now through external tools. Then you have Gemini from Google DeepMind. So, it has of course many versions. So, this is Pro 1.0 was very similar, I mean in terms of performance, to GPT 3.5, and Gemini Ultra 1.0 was very close to GPT 4, and then they had Pro 1.5 that can support very long inputs up to like 10 million tokens in context. They can support both image and video, and then can also generate images. And then you have Claude model, again very popular model. So, comes at the same level as GPT, Gemini, and so it can also take a very long context, can process images, and has shown very strong competitive results with GPT-4. So, these are some open and closed models, but not all, right. These are not exhaustive, just some representative models. Now, we will focus on what's new in terms of architecture in these models, right. So, by just reading the description of the architecture, we come up with certain terms like SWIGLU. So, they were using SWIGLU, so which is a gated linear unit variant. So, they use a different activation also. So, instead of using FFN and ReLU, they use a different activation and different unit, not FFN unit. Then they are using RMSNorm. So, instead of layer norm, they are using a different normalization. They use a bias and attention layer. We will briefly talk about that. And then positional embeddings, they use rope, so rotatory embeddings instead of the additive embeddings in sinusoidal that we studied. And they have been using mixture of experts, many of the models, instead of feed-forward network that we briefly covered earlier. So, we will focus on this part in this lecture. Okay. So, let us go back to the activation function. We will talk about two parts, the actual unit instead of FFN and the activation function. So, we talked about ReLU as has been the default activation function till now, but there are many variants that are there. Like ReLU, one problem is that it becomes 0 immediately in the negative direction. So, what about some other function that do not become 0, like leaky ReLU? So, when you are in the negative inputs, you do not make the output 0, but you can say scale it to a number that is less than 1, right. Like you can do max of alpha x and x. So, whenever x is negative, if alpha is less than 1, alpha x will be higher than x, right. So, you would in the negative direction, you will take alpha x. So, like if you take alpha equal to 0.1, it will have a very small value in the negative direction, but it will not be 0, right. And you can even make it parametric by saying this alpha we will learn, right. So, you can say alpha can be learned through backpropagation. So, that becomes parametric ReLU, right. So, it's computationally efficient and converges much faster than ReLU and then sigmoid and 10H, and it does not die, right. So, this is the leaky ReLU variant. Then you have the exponential linear unit. So, again a variant of ReLU. So, it combines all the benefit, like in x greater than 0 it remains x, but if x less than or equal to 0 it is alpha times e to the power x minus 1. So, you have an exponential term in the negative. So, you see the term looks like this. So, if it is greater than 0 it is same as ReLU, but here it is a very small value, right. So, alpha e to the power x minus 1. So, the problem here is that you need to compute exponential, right. So, every time you need to apply this activation function. So, this is ELU variant. Then you have SELU, scaled exponential linear unit, that seems to work better than ELU. So, it has a nice self normalizing property, and it has been shown that it can train deep networks without using batch norm if you use SELU activation. So, what is the formulation? So, it is very similar, except you have a lambda term to the positive direction, the negative you have again a lambda term, right, and this are typically the values that were found to work best of both alpha and lambda with this function. Okay. So, this is just SELU. Now, you have another one that has become very popular, is the Gaussian error linear unit, right. So, this idea came from dropout, right. So, typically what you do, see in ReLU what you do, whenever an input is greater than 0. So, in ReLU if the input is x is greater than 0, you multiply it by 1. Think like that. So, multiply by 1. If it is less than 0, you multiply by 0, right. That is what you do, right. Now, think about dropout. What you do, you have an input, you randomly multiply it by 0 or 1, right. So, this is what you do in dropout, right. Now, what if we multiply it by 0 1 depending on what is the input, right. So, we say, so we will say x times probability that x is less than or equal to x, is how often the value of x is less than equal to x, right. And now it's a cumulative thing, so you can see when the probability will keep on increasing as you increase x. So if x increases, so probability that x is less than equal to x will also increase, right. So that means for positive value you will have a higher probability of retaining, right, if you multiply by this. So if for the positive or the larger quantity, you will have multiply by a larger value, I mean always less than 1 anyway, and for negative value it will be much smaller value to multiply with. So that is an idea that behaves similar to the idea of ReLU, but now you can see, okay, it will be dependent on my how large my input is directly. So small values are more likely to be multiplied by 0 and large value will be more likely to be multiplied by 1, right. Now how do you compute it? So you say, okay, most of the times the data will be say Gaussian, so normal distribution, so mean, let us say mean 0, variance 1. So use that particular curve and say, if we have that curve, we know how to compute the probability that the value is less than equal to a particular point, right. So less than equal to this value or less than equal to this value, and you can do that by using the error function. So 1 plus error function of x by square root of 2. Now in the paper they had shown that you can approximate this and make it something like deterministic. Yeah. So they do many things. For example, first of all they are saying, okay, you randomly multiply a value by 0 or 1 depending on the particular value, and that you can take an expectation over randomness, and that is where you will get this. And now you will take an approximation for that, and you have a term like this, and this looks interesting. So x times sigmoid of some scalar multiplication of x, right. So that is the Gaussian error linear units, and this scalar is fully determined, right. So this is the unit that you are used a lot and has been shown how they are much more effective in practice. So now in recent models they have been the default models. So GALU, default activation function. Now there is another activation function, that is swish function. So this is, if you see, the formulation is very similar to the GALU, except that you have a term beta which can either be a constant or a tenable parameter, right. So this beta can be either a constant, like if you can put 1.72, it will start behaving like GALU. If you put it to be infinity, like if a very large beta, it behaves like ReLU, yeah. And for 1.72 it will behave like GALU, and similarly when shown for another beta value, it behaves like another activation function, and this is like beta is equal to 0.1, this is the value, right. So you can have it as a constant or a tenable parameter. Many times people use swish of 1, that means beta is value is 1. So many times you use beta is equal to 1 with swish activation function. So and lately these two activation function, GALU and swish, have been the most popular ones. Now, so this is the activation function. What is happening to the feed forward network that we talk about? What is the variation that people are using? So this is our original model. So now we may not have talked about the bias terms, but generally the original formulation comes with bias terms. So you have two matrices, W1, W2. So you have the input x, and you multiply by W1. Then you have a nonlinearity, right. So you have a nonlinearity. So it can be ReLU. So this is what max of 0 x W1 plus b, right. So this is x W1 plus b is the pre-activation, and then you apply ReLU on that. So you get this as the activation, and now you multiply this by W2, right. So this thing you multiply by W2 and plus another bias term B2, right. So this is our original FFN model. Now from T5 architecture, people found that these biases are not important. It's better if you remove the biases, it trains better. So this version has been very popular, that you don't use the bias terms. So it's more recent. So you say remove bias term, that's easy. You have max of x W1 0, this is the ReLU, and then you multiply with W2. So that is the FFN without the bias terms. And this you can connect with what do you mean by saying So you put bias in the attention, right? Remember we talked about Quen, this has bias in the attention layer. That means when you do the multiplication attention layer, QK transpose, you add the bias terms there, right? So that's what is the bias in the attention term. And you are removing bias from the FFN, but it seems that you can add bias to the attention layer. Now once you have it, you can say I can use other activations, right, other than ReLU that have become more popular. Like you can use GELU function. So then you can say, okay, my FFN with GALU without the bias terms would be GALU of XW1. So rather than using ReLU, you can use GALU, and then you multiply by W2, right? So it's a simple variation, and you can also use swish with beta equal to 1. So swish 1. So you can also use swish, right? So these are some variations with different activation functions, removing bias or not. And as I said, this is more recent that you do not put bias, and these two are much more recent. Now, so this is still retaining the FFN, but people have also tried to remove FFN, but tried some gated units, and this is what is called the gated linear units, right? So GLU. So what you do there is something different. So you have this X. So now you will create two linear projections, right? So you can have, so I have two matrices W and V. So earlier also I had two matrices, but now the operation is different. So first you do X times W plus B. So this is your X W plus B, and you also do another another projection. So you can call it, I am writing it like this for easy visualization, but something like this. So this is X V plus C. So you have two matrices again, W and V. So you have two matrices. Now what you will do, you will take the element wise product of them. Of course, you still want to put nonlinearity. So what you do, you put in one of the things. So in one of the projections, you do sigmoid or whatever you want to put, right? You can put ReLU also, but the original gated linear units had this sigmoid. So you have a sigmoid on this, and nothing, no activation here, and then you take an element wise dot product. So this is an element wise dot product. So it's a different variation. Okay. So earlier you were doing sequentially X, W, and then whatever you get, you put nonlinearity, and then you multiply by another matrix. Here you multiply both the matrix together with X, right? And to the output you do this dot product. Right. So this is the GLU unit. Now, so in the same paper they also created the variation where they call it bilinear. So you remove, get rid of this activation. So X W plus B and element wise dot product X V plus C, right? So it's a simple variation. Now the same units, the gated linear units, you can put with other activations apart from sigmoid. So you can put it with ReLU. So you get ReGLU. So you need this B and C are already there. So in the same parameters, so you have max of 0 X W plus B, element wise product with X V plus C, right? Just replacing sigmoid by ReLU. You can replace it by GALU, right? So this will be the formulation GEGLU, right? And then if you replace it by swish, this is what gives you swiglu that you have seen in this in these slides. So many architectures are using swiglu. What is that? So I'm using gated linear unit, and the activation here is swish activation with some beta, and this beta is typically set to 1. Right? So this is a swiglu compared to what we talked about in FFN. Okay. Now what is RMSNorm that we talked about? So you see, when we do layer normalization, so this is the formulation. So first of all, we have to center it to mean 0 and variance 1. This is the centering and scaling. So recenter and rescale to mean 0, variance 1, and then you have some learnable mean and variance. So you say this is my learnable mean and this is my learnable variance. So I accordingly scale them back, shift and scale back. This is the layer norm. So what they do in RMS norm. So in RMS norm, rather than doing this, they will not recenter it, but they will rescale it using the L2 norm. So they will take alpha times h by the L2 norm of the values. So, you can see this is just simply the L2 norm h1 square plus up to hd square root. So, you divide by that, right. So that the L2 norm is there. So, this is the normalization, and then you can now scale it and shift it, right. But there is no recentering happening like what you had in the layer norm. So, this is the RMS norm variation. Okay. So, this is like not too difficult, but I mean now once you have seen it, becomes easier to understand what is happening in the new architectures. Now, so we have not talked about yet other things like positional embeddings, and they are the one crucial part is how do I extend the current methods to very long sequences, right. So, we will talk about that in the next lecture, right. So, you can some references are like this survey that I have used, large language models survey, and also the book Foundations of Large Language Models that has given a lot of interesting details about these. We will use this book also in the next lecture. Okay. Thank you.